All right, we'll get started. Good evening, everyone. Thank you, Krishna Kumar, for joining. And I guess most of you are going to see in YouTube anyway. Uh, Good evening to you guys also. Uh, Today, what we are going to do is, as usual, we will go through whatever we discussed in this week's content, and we will solve few problems. And if you look at what we discussed in this week, it's going to be natural convection, condensation and boiling. Okay, and this in your final week 12, you will be discussing heat transfer. Okay, so let me check my recordings. All right. Um so uh, I think partly we discussed natural convection in the last week itself. We also kind of okay, we didn't solve any problems though. So we will solve one problem in natural convection today, and we will solve two problems in condensation. And that, yeah, basically we will solve three problems altogether today. Uh, so in natural convection, I think not entire topic is covered in the last week. So this week also contains two more lectures on natural convection. But anyway, for the sake of completeness, I will fully go through natural convection today, and uh, and then we will go through boiling and condensation. Then we'll solve the problems. Okay. So in natural convection, so the other convection mode is forced convection. The only difference between natural and forced is you do not have any forcing mechanism here. The temperature gradient itself is the forcing mechanism for the fluid to flow around, right? So the fluid moves because of the temperature gradient, and that is the important difference between natural convection and forced convection. And as usual, it brings with us complication that this momentum equation and the energy equations are coupled. Till still, till force convection, we did not have that problem. We solve the momentum equation separately. We'll get the velocity field, and then we'll substitute it in the energy equation. Now, the velocity field itself is as a result of temperature gradients. That is the complication that we have. So, um, this is the natural we studied especially for a vertical plate, a heated vertical plate. And when the gases are, let's say air is in contact with it, it gets heated up, and when it gets heated up, the density drops. And as it becomes lighter, it starts moving upward. Okay. So, and at the end of the plate, it has to go, it cannot go any more further up, so it has to turn away. So it cannot go inside, no penetration condition is there, so it turns around. And then as it goes away from the plate, it gets cools down. If it cools down, the density is going to rise. And if the density rises, it is going to start uh, you know uh, falling down. So that is what happened, and because of continuity, this process keeps on going, and that is what we are trying to model it. That is what we are trying to analyze. And for that, we have 2D incompressible flow equations: continuity, momentum, and energy. We have two momentum. We are not interested in z momentum. And uh, if we simplify this, um, here especially along y momentum, along y direction flow is happening, so we are interested in y momentum. In y momentum, we apply this boundary layer analysis approximation. Delta is very much less than h, and that is one approximation. The other approximation is the pressure gradient along the y direction, along the vertical direction. That is going to be purely based on statics. That is one approximation that we are making, although flow is moving around. This is also valid approximation because in a boundary layer analysis, we assume that dou p by dou x is along the flow direction is zero, or it's same as free stream pressure gradient. That is what we assume. Same thing here, the free stream is nothing but your bulk is not moving, so it's a static it's a fluid in a column. So fluid in a column has a pressure gradient of dp infinity by dy is rho infinity g. That's the thing. So you substitute that 2 over here, and then you simplify this. Your y momentum looks something like this. And then there is something called Boussinesq approximation that we make. Here the density is also a function of temperature. So the Boussinesq approximation says we have density everywhere, so we want to we do not want to complicate everything or every other term in the equation. We will just add the density as a function of temperature to the gravity term. So that is the Boussinesq approximation, and it is also, you perform a Taylor series expansion for density, and then you take only the first derivative, you ignore the higher order terms, and you express in terms of volumetric heat expansion coefficient, and then finally you will end up having this term for your source term, or the body force term. Now you will have this as your y momentum equation, and you can see that you have u velocity, you have v, and then you also have temperature in your momentum equation. So usually you do not see that in natural convection. You have temperature also in your momentum equation, and you perform non-dimensional analysis. When you perform non-dimensional, you will end up having non-dimensional numbers, and that is what you see here. This is nothing but your um this is this part. you you substitute here, you will end up having Reynolds number, and then the additional number that you have here is nothing but your Grashof number, okay, or Grashof number times Reynolds number square, okay. And based on this ratio, you will be able to say whether it's a natural convection or forced convection, or both the convection regimes are present. Both the convections are important. That is called mixed convection. Okay, that is what we stopped in previous week. In this week we did order of magnitude analysis to understand what is this. So at the end of the day, we need Nusselt number and its correlation with the Prandtl number, or what are the other things that is going to depend on. So that is the correlation that we need. That is a rough idea. How the heat transfer is going to happen is going to given by the Nusselt number. So here, for that we can simply do order of magnitude analysis, and in the order of magnitude analysis we have these three equations. This is the y momentum equation, continuity, and the energy equation. Now you perform this order of magnitude, we know how to do. So you take an reference scale u, v, delta, and h. Here the delta is thermal boundary layer thickness. So because we are interested in thermal boundary layer, that's why. Okay, and then you perform this analysis, you will end up having uh, three different scales: inertial scale, viscous scale, and buoyancy scale. Now based on which one is dominant, your Nusselt number is going to depend on that. Okay, so inertia versus buoyancy, when you do, you have something like this, and viscous versus buoyancy, when you do, you have something like this. Now the only thing is, when inertia and buoyancy are in the same order, then you have both Rayleigh number and Prandtl number here. And in terms of h and delta t, so we still don't know which of these is going to play an important role. So we take a two different case. One is Prandtl number is very much greater. If the Prandtl number is greater, we know that inertia by buoyancy is going to be very much less than viscous by buoyancy. And if that is the case, then um, viscous will be in the order of buoyancy, so within the thermal boundary layer. So if for Prandtl number very much greater than 1, you will have delta T by H to be dependent on only Rayleigh number. And but delta T by H is not we want Nusselt number, and Nusselt number we can find it by calculating the heat balance at the surface. And when you do that, you can find the Nusselt number to be a function of Rayleigh number power 1 by 4. Okay, so this is the representation of how the boundary layer look for Prandtl number very much greater than 1. Okay, so you will have delta T to be smaller than delta. So the flow boundary layer, or uh, what do you call, momentum boundary layer thickness, would be greater than thermal boundary layer thickness. That is what you see here. So far so good, there's no problem. Now here we do not have Prandtl number. Nusselt number doesn't depend on Prandtl number. Now, but uh, the momentum boundary layer thickness or the thermal boundary layers thickness is going to depend on Prandtl number, and that dependence is PR power half. That's what we derived. Okay, and that is going to happen only outside the uh, thermal boundary layer, because outside the thermal boundary layer you do not have any temperature gradient, so buoyancy effect will not be there. If the buoyancy effect is not there, then it's going to be only inertia and viscous. So outside this layer you are going to have inertia is going to be of the same order of viscous, so that is how you end up having this relation. Okay, now if the Prandtl number is very much less than 1, then inertia will be in the order of buoyancy, and when you do that analysis you will end up having Nusselt number to be a function of both Rayleigh number and Prandtl number. But the thing here is this Prandtl number here is not delta by delta t. Okay, uh, the not the momentum boundary layer. So here there is going to be momentum until the temperature gradient is present, right? So if delta t is present, then delta is going to be almost equal to delta t, at least for this case. Okay, so the Prandtl number here is going to depend. It's actually a representation of a viscous layer's thickness. Okay, so in the viscous layer, so near the wall you will have a lot of viscous forces, you cannot ignore that. Even though in the bulk you have inertial scale equivalent to buoyancy scale, near the wall viscous will always be dominant. Okay, so when that viscous is dominant, you can equate viscous with buoyancy, and when you do that you will end up having a boundary layer thickness called viscous layer thickness, and that scales as Prandtl number power 1 by 2. So that is what here the Prandtl number represents the uh, viscous layers thickness. Okay, and you can also visualize it. So Prandtl number is nothing but momentum diffusivity by thermal diffusivity, right? So momentum diffusivity is actually dynamic viscosity, or in terms of viscosity, or it is a representative of viscous uh, nature of the fluid. Now if I say inertia is goes as buoyancy, then the viscous becomes viscous doesn't viscous is no more important, right? So viscous, wherever the viscous is important, that's where the Prandtl number effect will be there. But we are studying the heat transfer subject, so we need we know that the Prandtl number is going to affect. So that is what our analysis also said. Then uh, where does this mismatch happens is because this Prandtl number now it's a representation of viscous layer. Okay, so even though we equate inertia, goes as buoyancy, we still got the Prandtl number, where Prandtl number is a function of viscosity. Okay, now that is coming from the viscous layer, not from the bulk. That is what I wanted to clarify here, and that's why you have Prandtl number here. Prandtl number is an indicator of delta V by delta T rather than delta by delta T. Okay. Now you can also perform by integral method. I am going to leave it up to you to do that. You can also come up with the exact function of Nusselt number equal to as a function of Prandtl number and Rayleigh number. Okay. All right, so this is where we stopped natural convection. They similarly, like Dittus-Boelter for forced convection, we can also have similar correlations which is derived from experiments uh, by various researchers. So there are different correlations that you can use, uh, but we are not covering them in this subject, okay, or in this course. Then we jump to condensation. So condensation, we know that there are two kinds of condensation: film condensation and drop-wise condensation. In film condensation, you will develop a film of water uh, on a vertical plate, or any surface, as because of condensation. So initially there will be bare surface, and as condensation happens, there will be a film of water developing on the surface, and depending upon whether it is horizontal or vertical, it's going to start flowing down. Okay, that's why we call it a film condensation, and it's also a flow problem. Fluid is going out. So similarly, you have a vertical plate, and condensation happens, and it starts, and it forms here. Once it forms, it starts, dropping down because of gravity, basically. So in your equations, you should have gravity. Without that, your analysis will not work. Okay. To solve this kinds of problem, there is something called Nusselt solution. So for that, we'll make certain approximations in the governing equations. Once you make those approximations, you will be able to, derive an explicit expression for, heat transfer coefficient or Nusselt number. Okay. So the Nusselt solution goes like this. You have a momentum equation. Again, these are boundary layer development, so you can use boundary layer approximation. And here, so in natural convection, we took this axis, vertical axis, as y. Here we are going to go back. We are going to take the vertical axis as x. So you ideally will not have y momentum equation, or y momentum equation is trivially satisfied, and it gives you that pressure gradient along y direction is 0. Okay. And again, as I said, we need to have uh, gravity, and the pressure term is going to take care of that. So the pressure gradient along the x is going to be simply fluid statics, and that is going to come from rho g. Okay. Now we also have the body source term, and then this is the pressure gradient, which become fluid static formulation. Now if you simplify this, it becomes simply uh, a second order ODE, and at the end you will end up having this kind of velocity profile. This is the velocity profile you are going to have for this problem. Okay. So it's going to be a function of x. Sorry, it's going to be a function of y. Okay. And also delta, and delta is going to be a function of x. So this is a function of x, and it's also a function of y. Okay. Now velocity profile is fine. We need what is the total heat transfer because of this condensation, right? And also what is the net mass flow rate of condensation. Yeah, rate of condensation, basically we need it. So for that, we have this mass conservation for any elemental, you know strip over here. So the mass is going to be conserved, but in addition, you also have some condensation happening on the film. So that's why your mass conservation looks something like this. And rate of condensation is going to be simply the heat transfer rate divided by total heat transfer rate divided by the latent heat of what you call vaporization or condensation here. So that is HFG. Now you simplify them, you substitute these, and then uh, you know we know that mass flow rate is from 0 to delta. That's why, and it's also a function of velocity. So you have this as an expression for mass flow rate, and then you substitute them, and then you integrate them, and then you will finally end up having delta to be a function of x, which is going to be some complicated function like this mu k. Tv is nothing but the vapor saturation temperature, and Tw is nothing but your uh, surface temperature. Okay. um, the condenser surface temperature. Now we are interested in H, heat transfer coefficient. So we know H is uh, here you can find H to be K by delta here. So Hx is simply this is the convective heat transfer coefficient because of condensation. Okay. And then this is the function of x. Now you can integrate with respect to for any, if you want an average convective heat transfer coefficient, you can integrate it, and we all know the formula. So that would be simply uh, so for plate of length L, it's going to be 4 by 3 times heat transfer coefficient at length L. Okay. So this is what it is, and then you have, if you have an inclined plate, your the source term is going to modify. If the source term modifies like this, then it becomes going to be you have an integrated also, so it's going to be some cos theta power 1 by 4 will be there. Okay, so that analysis you can do. So the same thing, only thing is you will have, instead of g, you will have g sine theta. Yeah, here you will have g sine theta, and then you complete the analysis, you will end up having that relation too. And then professor discussed different places where you will be using this condensation and what are different kinds of condensation you can have. And for all these you have similarly, like we have this H, uh, people have developed correlations from the experiments for different tube geometries. Here it's just a vertical plate. If it is a circular tube, how the heat transfer coefficient will vary. If it is a bunch of tubes arranged together, how that is going to affect your heat transfer coefficient. All these things people have done experiments, and there are correlation graphs available, which you can use it to find the heat transfer coefficient. Again, we are not covering them here. Okay. Um, Similarly, boiling is even more complicated process. We are just touching it, that it is going to depend on pressure, temperature, and surface tension also, because you have bubbles. Bubbles are, but they form bubbles because of surface tension. Inside there will be a different pressure. Outside there will be a different pressure. The only way the bubble can sustain is this pressure balance is balanced by the surface tension process forces on the bubble. Okay, bubble surface. So the bubble growth, collapse, all these things is going to depend on this surface tension. Uh, and they similarly, when you have such setup, you have heating, and then you know gases forming and going on. You are going to have different regimes. Initially, you will have like a free convection kind of regime, uh, where you will have small bubbles forming, and it goes, comes back. All these things, a simple bubble motion will happen, and as it goes, that is called free convection, and then it enters into something called nucleate boiling. And here you will have isolated bubbles, and then the isolated bubbles forms, and it forms a jet column like this, and at some point it reaches the maximum heat flux. That's a maximum heat flux you can uh, it can have. Okay, so that is the critical heat flux, and after that it goes through a transition to film boiling. So film boiling is nothing but here, like we have film condensation, there will be a vapor film on top of the heating surface. So that is going to, the onset of film boiling is, we call it Leidenfrost point, and that place you have very low heat flux, because the film has vapor phase, and gas phase we know thermal conductivity is very low, and that's why you have low heat flux. So it acts as a resistance. That's why you have low heat flux, and then after that it's going to again continue to rise it in its own fashion. Okay, so this is the pool boiling curve. We didn't go much in detail, but yeah. And heat exchanges, that's going to be uh, a topic for next week. Okay, all right. Yeah, I think we discussed these two things in detail today. Just a quick recap of what has been taught. Now we will go on and solve a problem. So the first problem is going to be on natural convection. Uh, and as usual, if you have any questions, you feel free to stop me anytime and ask your questions. Okay. All right. So the first question is about flat plate boundary layer equation for natural convection. Is given as these. So this is the mass, this is the y momentum equation, and this is the energy equation. This is what we solved during the class. Now, the dependence of Nusselt number and various flow can be determined by order of magnitude analysis. That's what we did. For the low Prandtl number fluid, which means Prandtl number very much less than 1, answer the following questions. Okay, so what is the dependence of Nusselt number on Rayleigh number and Prandtl number? So this is the question. So for Prandtl number very much less than 1, for Prandtl number very much greater than 1, it's going, Nusselt number is going to depend on only Rayleigh number. Here it's going to depend on both Rayleigh number and Prandtl number, right? uh, if we go back, Nusselt number very much less than 1, is going to depend on both Rayleigh number and Prandtl number. Now, so you can write Nusselt number. I mean, you can derive it, but I'm not going to do it because we already did it. So Rayleigh number power 1 by 4, Prandtl number power 1 by 4. So now let's try to modify this thing to answer the second question. Second question is how the Nusselt number value varies when all the parameters are kept same except the length scale is increased by a factor of 2 and thermal diffusivity is half. So what is length scale? So length scale is nothing but this h, right? So that is the height of the vertical plate. This length scale they are increasing. So initially it was, let's say, h1. Now let's say h2 is like 2 times h1, and thermal diffusivity is half. So something like alpha 2 is alpha 1 by 2. So then how Nusselt number 2 is going to vary? So what is the functional dependence of Nusselt number as a function of the whole Nusselt number is what they are asking. Okay. So for that we need to know how Rayleigh number looks and Prandtl number. Rayleigh number is G beta delta T h cube by nu times alpha. I guess it's right. So G beta delta T h cube by mu alpha. Okay, this is Rayleigh number, and Prandtl number is nothing but mu by alpha, right? So now we'll just substitute them here. So Nusselt number is G beta delta T h cube by mu alpha power 1 by 4 times mu by alpha power 1 by 4. Okay. All right. Now this h is going to be 2 times h, so it's going to be let's say if you substitute them, let's say nu2 is going to be G beta, okay, G beta delta T h1 cube divided by mu1 alpha, mu alpha 1 times it's going to be 2 cube divided by it's 1 by 2 alpha 1 by 2, right, whole power 1 by 4. But Prandtl number also depends on alpha, so it's going to be mu by alpha 1 times divided by 2, so I can write this as 1 by 2 by 4. So this is going to be simply Rayleigh number 1 times, so you can write this as nu1 times 2 cube by 1 by 2, which is going to be 2 power 4 power 1 by 4 times 2 power 1 by 4, which is going to be 2 times 2 power 0.25 times nu1. So this is how this is going to vary. Okay, so you need to be a little bit careful. You know you would expect these kinds of questions in your final exam. Okay, and now the second question is if the kinematic viscosity is increased by a factor of 2. So here only the kinematic viscosity is increased by factor of 2. What happens, you have mu power 1 by 4 here. Here numerator it's mu power 1 by 4. So ideally you do not have any kinematic viscosity dependence if you look at this, right? So you can just directly remove these two. So whether you even if you change, this is going to be not changing. Okay, and this is as a function of 2 times 2 power 0.25. Okay, Now the third is if the length scale and thermal diffusivity both are increased by factor of 16. Okay, so both length scale and thermal diffusivity. So H2 is 16 times H1 and thermal diffusivity, right? Alpha 2 is 16 times alpha 1. Then how would this increase? So, so you can say Nusselt number is a function of H power 3 by 4 divided by alpha power 1 by 4 times alpha power 1 by 4, which is going to be alpha power 1 by 2. Okay, yeah. So this is the dependence on H and alpha. Other things are remaining same, so I removed them. So this is going to be simply, so Nu2 you can write it as 16 power 3 by 4 divided by 16 power 1 by 2 times Nu1. Okay, so how much this is going to be? So you can write, so I can write this as 16 power 3 by 4 divided by 16 power 1 by 4 times 16 power 1 by 4. Now this can be written as 16 power 2 by 4 by 16 power 1 by 4. By 4 is half. Then this is going to be 4 divided by, this is going to be 2. So it's going to be 2 times. So when you increase 16 times the heat, H, and 16 times the alpha, you are going to increase the Nusselt number by 2 times. Okay, just the simple manipulations. All right, I hope this is straightforward. Shouldn't be a much problem. If you have any questions, please let me know. Now the second question is in condensation. Okay, uh, I think we haven't solved any questions even in the lectures, so I thought I will give you an idea of how. So you need to have some sense of numbers when you talk about condensation. What is the number range that we are talking about when you say heat transfer due to condensation? Okay, that's why I thought I will solve one problem. So this problem is like you have a 3 meter cross 3 meter vertical plate, same as what we studied. Um, so we did for vertical plate. So I refrain myself in selecting a problems which involves vertical plate. So we didn't do any you know a tube, condensation over a tube, right? So for that the formulas will be almost same, but there will be an additional factor to it. Okay, so those things you can find it in a heat transfer textbook. But here we are going to study about the vertical plate. You have 3 meter cross 3 meter vertical plate exposed to one side to a saturated steam at atmospheric pressure. So based on pressure, your saturated temperature will vary. In atmospheric pressure, it's 100 degrees Celsius, so there's no problem. Um, saturated steam at atmospheric pressure, and on the other side to the cooling water that maintains the plate temperature at 50 degree Celsius. Okay, so the water is the steam is getting condensed on the plate, and the plate is at 50 degrees Celsius. The steam is at 100 degrees Celsius. Okay, now what is the rate of heat transfer to the coolant? So, what do they mean by that is the to maintain the temperature at 50 degrees Celsius, there is a coolant which is going to uh, continuously take away the heat from the surface. Okay, so that what is the rate of heat transfer to that coolant? So that is nothing but your rate of condensation. Okay, I mean mass flow rate of condensation times the latent heat of vaporization or latent heat of condensation. Okay, so that is what we are first we should find out. Okay, this is what we need to find out at A. And B is if the plate are inclined by an angle theta, how your heat transfer coefficient or how your heat total rate of heat transfer and the rate at which steam condenses will change is what they are asking. Okay, so I have taken properties here, but these properties can be taken from your steam tables. So it's a atmospheric pressure. So for example, at 1 bar and 1 atmosphere, not much difference. So 1 bar, you have Tsat to be, maybe I will write just 1 atmosphere. At 1 atmosphere, Tsat is 100 degrees Celsius, and your heat transfer, the HFG, which is latent heat of vaporization, is 2257 kilojoules per kg. Okay, and uh, your steam tables will have specific volume. You invert the specific volume, you will end up having the density. Okay, density of the vapor. So this is what is getting cooled. Now, the liquid properties at some temperature here, 75 degrees Celsius is given. For that, you have these properties. Now, we need to find out what is the rate of heat transfer. So, the rate of heat transfer to the coolant. So, for example, maybe I will draw a sketch here so that you will understand it better. So, here you have this condensation happening, and you know, there's a fluid, it has developed, and then it continuously flows down. So here the temperature is Tv, and the temperature is nothing but this 100 degrees Celsius. Here the temperature, let's say Ts, is 50 degrees Celsius. Okay, but this is maintained by, you have coolant which is going to come, it's going to cool the surface. So this is a coolant. So there will be a heat transfer from here to here, Q, because this is condensing, it is going to give up energy. So this Q is what we need to find out. This Q is what being carried away by the coolant. So if it has to be maintained at 50 degrees Celsius, you should have some coolant to cool the surface continuously. So this Q is nothing but your total heat of total heat transfer rate due to condensation, and that we can express it as HA times Ts minus, or the other way, Tv minus Ts. Okay, the is that what is we, okay, Tv and Tw we wrote is Tw, so it's Tv and Tw, and this is nothing but your m dot of condensation times HFG. Okay, so we need to find both Q and we need to find m dot C. So once you find Q, you can find m dot C. So for that, we know area already? We know already, right? So you have, this is 3 meters. So the length is 3 meters, and then you have a breadth which is also 3 meters. So the total area exposed is actually 3 times 3, which is 9 meters square. And Tv minus Tw is 100 minus 50, which is 50 degree Celsius or 50 Kelvin. So your Q is nothing but H times 9 into 50. So only thing is we need to find H. So this is like 450 H watts. So we need to find H, and that is what we derived here, right? Heat transfer coefficient, which is a function of, here we have two things. One is heat transfer coefficient as a function of X. We also have average heat transfer coefficient. So we want the overall average heat transfer coefficient because we need the total heat transfer rate. Okay, so we defined it as HL bar, so we will be consistent with that notation and say HL bar. Okay, and HL bar is actually 4 by 3 times HL, where HL is nothing but rho L times rho L minus rho V times K G H of G K Q K Q G H of G divided by, I guess there's a mu, okay, 4 times mu times TV minus TW times, you have X, but we want at length L. Okay, so now I think we have all the parameters. We just need to substitute in this relation. What is it going to be? So HL is going to be 4 by 3 times, so rho L. Now this rho L mu K, this K, all these things is a liquid property. Okay, because heat transfer is happening from here to here, and the heat transfer coefficient is, liquid is what is in contact with the surface, right? So when liquid is in contact with the surface, liquid's property is what we need to use. And even our entire Navier-Stokes equation is written for liquid, not for the vapor. So all these properties are liquid properties. Okay, now the liquid has temperatures varying, so liquid property has to be evaluated at some mean temperature. Here the mean temperature is going to be TV plus TW by 2, which is nothing but 100 plus 50 by 2 is 75 degrees Celsius. And what I took is, I took the properties to be at 75 degrees Celsius, so we can just easily take it. Okay, so Royal is 975 times 975 minus rho V. Rho V is it's a vapor density, so it's 0.5903. Actually we can, because of this big difference in the density between rho L and rho V, we can actually write this term as simply rho L, so it's not going to change much. I think there should be another 1 by 4 factor here times KL. K of liquid is 0.668 square, sorry, cube, times gravity 9.81 times HFG 2257 kilojoules per kg. 2257 into 10 power 3, because it's in kilojoules per kg. Okay, divided by 4 into viscosity is 375 times 10 power minus 6 into TV minus TW, it's 100 minus 50 times length is L. L is nothing but 3 meters, whole power n by 3. Now you guys can simplify and let me know what the answer is. It's a lot of terms we have here. Okay, so my calculation says something like 3063.46 watt per meter square Kelvin. Now I don't know whether this is right, but the order of magnitude seems like it's an. So for the condensation problems, you will have heat transfer coefficients in like thousands. Okay, so usually you do not reach that in a forced convection. Maximum you will have 250, 300, or 500 watt per meter square Kelvin is what you will have when you have a forced convection in practical applications. But when you have condensation, your heat transfer coefficient will be very high. This is purely because of the latent heat that it gets released while condensing. Okay, that's the reason for this. So it's going to be in the orders of thousands. So it will be even more than this, 5,000s or something like that in practical applications. Okay, all right. For this problem, let's find out Q. Q is nothing but we just simplified 450 times HL bar, which is 450 times 3063.46. How much is this? It's something like 1378.55 kilowatt. Okay, see, you can note this. This is in kilowatts. Till now we have been, dealing with only watts. Now you will have kilowatts. Okay. So condensation problems have, that's why condensation is like very high heat transfer rate appliances. So if you have a condensation happening in one of your appliances, you are going to have very high heat transfer rates. And people also sometimes prefer to have that when you have to cool it down a large uh, chunk of mass from high temperature to low temperature. Okay. All right. We also need to find m dot c. M dot c is nothing but q divided by h of g. So q is 1378.55 into 10 power 3 divided by h of g is 2257 times 10 power 3. 2257, or what is it? Yeah. Okay. Now this is going to be some zero point 0.5 kilograms, I guess. 57, 10 power. So it's like 0.61 kilograms per second. So this is the rate of condensation. Okay. So this is fine. This is for vertical plate. Now if you have an inclined plate, they itself gave a hint. For plates inclined at an angle theta from the vertical, the ratio of average convection coefficient for inclined plate to that of vertical plate may be approximated as cos theta power 1 by 4. Okay. Oh, okay. So now for inclined plate, the ratio of heat transfer of vertical by inclined is may be approximated as cos theta power 1 by 4. Inclined plate to that of vertical plate, not vertical by inclined. It's other way. Inclined by vertical is going to be cos theta power 1 by 4. Okay. And if 3 cross 3 meter plate is inclined at 30 degrees from the vertical, what are the rates of heat transfer and condensation? So we just need to find if it is the theta is 30 degree, we can use the h vertical that we just found out. And then hi is going to be cos 30 power 1 by 4 times hv is going to be cos 30 degrees power 1 by 4 times hv is 3063.46. 3063.46. Okay, so it's going to be less than 3063 because cos 30 is less than 1. Power 1 by 4 times 3063.46. So this comes out to be around 2955.25 watt per meter square Kelvin. Okay, this is the heat transfer coefficient in your inclined plate. Now similarly we can find the rate of heat transfer, which is going to be hi times a times tv minus tw Okay. Now, does A change? Just because it's an incline, the area available for condensation is still remains same, right? So A times TV minus TW doesn't change. So uh, we can put the same numbers over there. It's going to be 2955.25 times area is 3 cross 3 times 50. Okay, or 450 times, you can multiply these two and you will end up having 1329.86. So please check these numbers whether these are right, times kilowatt. Okay, so it's going to be a little bit lesser than what we got here. So here we got 1378 kilowatt, here you have 1329 kilowatt, so it's like 50 kilowatts less, around 50. Similarly, you can find the condensation rate, which is going to be Q divided by HFG, which is 1329.86 into 10 power 3 divided by 2257 times 10 power 3. Now, this is also going to be slightly lesser than 0.61. Yeah, it's going to be 0.589 kilograms per second. So because we have an inclined plate, our heat transfer rate and the rate of condensation has been, it's a little bit lesser. Okay, so vertical plate will have higher rate of heat transfer. It's because when the plate is vertical, you can drain away all the fluid, and the film thickness will be a little bit lesser. Okay, if the film thickness is lesser, then your resistance is less. So resistance is less, heat transfer rate is high. So you should remove. That's what people do usually. uh, they coat the surface with a different hydrophobic coatings in such a way that it will not form film at all. Okay, it will still form droplets as big as possible, and then they drain it out. Once it drains, again the bare surface will be available for condensation. So those kinds of techniques people are working on in order to avoid film wise condensation. So if the film wise condensation is avoided, so this rate of heat transfer is going to be even higher. Okay, this heat transfer coefficient will be even higher for drop wise condensation. All right, I guess this is clear to everyone. If not, please stop me anytime. No problem. So one more problem I have here. This is also related to condensation. um, it's it also gives you a little bit idea of heat exchanger too. But anyway, I'm not going to get into heat exchanger. So uh, we'll just talk about condensation here. Okay, I hope there's no doubt still now. So the third problem is you have a saturated steam at zero point 0.2 bar. This is not at 1 bar. So if your steam is at zero point 0.2 bar, your saturation temperature will be different now. Okay, it will no more be 100 degrees Celsius. It will be less than that. So that temperature you can get it from your steam tables. Now, saturated steam of zero point 0.2 bar condenses with a convection coefficient of 600 watt per meter square Kelvin. Um, so the condensation heat transfer coefficient is already given. So you no need to find out Tsat. You no need to perform this big equation. I mean big formula you don't need to do. So they have already given it is 6000 watt per meter square Kelvin. Okay. On the outside of a brass tube. Okay, it's a brass tube. It's a tube having inner and outer diameters. The convection coefficient for water flowing inside the tube is 5000 watt per meter square Kelvin. Okay, estimate the steam condensation rate per unit length of the tube when mean water temperature is 30 degrees Celsius. Okay, so which means, so let me draw the diagram so that it will be easy for you to understand. So it's a How do I draw this? Let me draw it in a vertical axis. So it's a tube. Okay. It's a brass tube whose inner diameter is 16 mm, then radius is 8 mm, and outer diameter is 19 mm, then radius would be something like 9.5 mm. So you can call this Ri, you can call this R0. Okay, this is a brass tube. So now the steam is outside. Actually, steam is a hot fluid. So probably I should have used red here also. I think I should change the colors. Anyway, here the steam is hot and the steam vapor temperature is some Tsat. Okay, let's ignore that. And the steam is going to condense here on the tube surface, outer surface of the tube. And that heat transfer coefficient is given. H condensation is given, which is around 6000 watts per meter square Kelvin. So this heat is carried away by the what is flowing inside. I think water is flowing inside. Yeah. So this heat is carried away by the water which is flowing inside. So that is going to take the heat coming from the condensation, and that H, let me call it I, is 5000 watt per meter square Kelvin. Okay. And the temperature of the water is 30 degrees Celsius. Now we need to find out what is the steam condensation rate per unit length of this tube. This is what we need to find out. Okay. The problem partially simplified because H is given. So you can write the rate, heat transfer rate due to condensation to be simply H times area times TV minus T wall, right? Here it is going to be uh, what are you going to write? So maybe I should write. So this is going to be T outer surface. So outer surface of the brass. So I'm going to write T naught, and this is going to be inner surface is going to be Ti. Where will I write that? Ti, and inside the water liquid is T infinity, let's say, and outside the steam temperature is TV. Okay. So these kinds of problem, we solved it while we were studying probably the resistance network. When we draw, we solve these kinds of problem. But there it was not condensation. Instead, it was like just some fluid is going on the outside and it has some heat transfer coefficient, right? So here it is going to be simply condensation. That's all. There is not much of a complication here. The mode of heat transfer here is condensation happening on the outer side. Inside again it's a normal convection. Now this H is given, which is like H condensation is given. You need to know area of the surface, that is going to be simply outer surface area times TV minus T naught. But we don't know the T naught, right? We don't know T naught, we don't know Ti. Only thing we know is T infinity and TV. TV we can find out. TV from steam tables you can find out. From steam tables for pressure to be 0.2 bar. So if you check the steam tables, you will end up having TV to be I guess it's around 60 degrees Celsius. Okay. So outside the vapor temperature is at 60 degrees Celsius, inside it's 30 degrees Celsius. The water temperature flowing inside. So that's the scenario given. But so we don't know T naught or Ti. So what we are going to do is you know, uh, we don't also need to necessarily find out the uh, temperatures in between. So we can just consider a resistance network for this. You will have initially you will have, let's say, T infinity water, and then you have a convection coefficient Hi. This is convection, which is going to be 1 divided by HIAI, right? Inner surface area. And uh, you have a conduction resistance along the brass tube. mm, Conduction in brass tube. This is going to be Ti, and this is going to be T naught. And from T naught, the heat transfer is going to be condensation. This is going to be your condensation. This is at TV. Okay, this is going to be 1 divided by H naught into A naught. Here H naught is nothing but H condensation. Okay, here the conduction in the brass tube is, since it's a cylindrical geometry, you are going to have the logarithm formula. So let's say I can write now the heat transfer to be simply TV minus T infinity, whose temperatures we know, divided by total resistance. And the total resistance is going to be R convection, water convection in the inside of the tube, plus R conduction in the brass tube, plus R condensation. Okay, and this is going to be 1 divided by HIAI plus in logarithm of R naught by Ri divided by 2 pi KL, plus condensation is 1 divided by H condensation A naught. And we were asked to do it for per unit length, so let's take a unit length approximation here. So this is going to be 1 divided by Hi is 5000. So if it is 5000 times area, inner surface area is going to be 2 pi Ri times the length here is 1 meter. So 2 pi into Ri is 8 mm, 8 into 10 power minus 3, plus logarithm of 9.5 by 8 divided by 2 pi into K. So K of brass, we need K of brass. So K of brass is 110 watt per meter Kelvin. Okay, so 110 times 1 plus 1 divided by H condensation is 6000. 6000 into 2 pi into R naught, which is 9.5 times 10 power minus 3. Okay, so now you find R total, you substitute in Q, you will end up having heat transfer rate. But what we need is steam condensation rate, which is nothing but divided by HFG. Okay, so let's first find out what is R total. Sorry. R total is going to be if you guys calculate it, please let me know. 5000 into 2 pi 8. The first part is 3.9789 10 power minus 3 this one 2.486 into 10 power minus 4 plus this 2.7922 to 10 power minus 3. Okay. Total is something like 7.0197 to 10 power minus 3. This will be Kelvin per watt. Okay. Now you substitute them. Q is TV is 60. That's the saturation temperature at 0.2 bar. 60 minus T infinity is 30 divided by 7.0197 power minus 3. So this would be around 4274 watts, or 4.274 kilowatt. So this is the total heat transfer rate. Now condensation rate is this total heat transfer divided by HFG. So we need to know HFG at HFG at 0.2 bar. This also you can obtain from steam tables, or it is not going to be that much different from 1 bar. So it's going to be around 2357 kilojoules per kg. Okay, so let's say I will substitute it here, 4.274 into 10 power 3 divided by 2357 into 10 power 3. This will be 1.81 into 10 power minus 3 kilograms per second, or 1.81 grams per second. So this is how you find m dot here when you have multiple fluids flowing in between. Okay, so this one will lead to something called overall heat transfer coefficient that you will study in your heat exchangers. So this is not just true for condensation, you can also have convection here. When you have convection here, you will end up having something called overall heat transfer coefficient. Basically it's nothing but 1 by R total is the overall heat transfer coefficient. This you will study in the upcoming week, the next week. Okay, all right. Any questions till now? So we solved one natural convection problem and two condensation problems, although one is more basic, like basic convection type problem, but it requires you to use steam tables to find some properties and input it. The other is finding heat transfer coefficient from the given properties. A natural convection, as usual, we studied what are the dependents. So similarly, you can also have, if the Prandtl number is greater than 1, then you do not have a Prandtl number dependence on the Nusselt number, and your analysis would change a bit. So yeah, if these kinds of questions are asked, please be a little bit careful. Write down the entire formula so that it will be easy for you to quickly reach the final answer. All right, any questions? Thank you, Avinash and Mustafa, for joining. If you have...
Sir,
Yes.
shall we get the transcript of the recorded videos?
Transcript of the recorded videos.
Actually, in some NPTEL course, transcript is giving.
Uh,
Lecture, sir.
the lecture videos, right?
Ah, yeah,
Yes,
lecture
sir.
videos.
Lecture video.
Transcript.
Um, doesn't the YouTube automatically gives you the transcript?
No, no, not giving. Actually, I tried, but in another courses they are giving.
Yeah,
They
yeah,
in
yeah. I think this course is. Let's see.
actually video
Oh, it's
lecture.
available. Okay,
Sorry.
it's available. So instead of, I mean, in the NPTEL website, you do not have, but there
Yeah.
is another website here. Uh, let's see. Let me check. Let's say condensation, English transcript. Oh, it's I don't think so. It's available, Mustafa. For this, I think for this course we don't have. Oh, for some lectures we have, some lectures we don't have.
It's available. Okay, okay, okay. How I will get the it is transcript of all the videos. Actually, total 60 videos now.
Yeah,
Total.
yeah,
I
yeah,
put
yeah.
60 videos. Actually, it is, for repeating, here repeating is not possible. 60 video now.
Mm-hmm.
Transcript is ready. Once we any doubt, we will clear within by watching videos. No problem.
Okay, okay. See, actually, I will tell you. There is this website you can check this. Maybe I will copy this.
Great. Okay.
Okay, maybe I will copy it and put it in my
Uh,
this thing so that it will be easy for you to access. Uh, okay, you check this website. In this, there are few lectures which you can have transcripts. Okay, so for
Okay.
some lectures you don't have.
Previously, in below lectures, there is a link is there from which we getting the recorded video, this recorded video and solved answers now. There is
Mm-hmm.
also they were providing transcript also.
Yeah, but I does this course doesn't have, I guess.
This course.
This
Oh
course doesn't
yeah.
have actually.
Okay, okay, okay.
So there are
If it's
some.
available, okay, if it's available, please add with this. Okay.
Yeah, yeah, sure, but I don't think
Is,
so. It's
is there
available.
is there is there any other choice within you?
Mm-hmm.
Please share with the along with that links.
So that's what
There
I'm
is a
telling.
link.
Yeah,
There is a
yeah.
Excel format now. That Excel format. If we are clicking on this link, we will getting transcript some courses. We are previously have done hydrogen storage course. There is a transcript is there. In other scholars are taking another course. They are getting transcript.
Yes, yes,
They
Mustafa,
are, they
I'm
are
aware
taken
of that.
easily.
Yeah, yeah, I'm aware of
Hmm.
that. Uh, but for this
Hmm.
course, when they recorded, they made transcripts for some lectures. They didn't make it for some lectures. Okay, so if you go through this
Okay, it's
link,
available with her.
yeah, that's what I'm sharing with you.
Hmm.
You go to this
Hmm.
website. Okay, in this website,
Okay.
in this website, it will look something like this. This is the website. In that you have downloads. In downloads you have transcripts, right? So for each lecture, so let's say 1D steady state conduction, uh, so you have transcript here. Okay,
Okay.
this way you can access it. Okay, this is, but for some lectures you do not have. Okay, for that I think
Okay. Okay.
you need to read the you need to see the video. Okay, uh, but for some
Okay.
lectures we don't have. That's the thing.
Most of the people, most of them will be useful. No problem.
Yeah, most of them will be there in this website.
Okay.
Please access it. Okay.
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 Actually, also in assignment 8 and 9, and marks are not updated.
Oh,
There
okay.
is a technical issue. There was a technical issues.
You haven't
These
received
are not
any email
rectified.
reply from NPTEL?
No, no, no,
Okay.
no,
Okay,
no.
then I will write the email today. I will send it to professor
8
and
and
talk
9
with him.
assignment. 8 and 9 assignment.
Sure.
Okay.
All right. Any other questions?
Sir, the Steam table will
No,
provided
no,
with
no.
the exam, sir.
So yeah, you don't need to worry about it. Steam tables, either Steam tables we will provide, or we might even, so like today I gave you the properties, right? So similarly, properties will be given to you uh,
Okay, sir.
in the exam. So don't worry about it.
Sir, for calculator, they are providing an on-screen
Yeah,
calculator.
on-screen calculator will be there. Yeah,
Yeah, okay, sir.
yeah. All right. Any other questions?
No, no, okay, okay, thanks.
All right. Thank you, Mustafa. Thank you, Avinash, for joining. If not, we will meet next week. Okay.
Okay, sir. Thank you, sir.
All right. Bye bye.